I'm Liang Du. So I've spent all of my professional life at Monash University working predominantly on the topic of fiber nonlinearity. So today I'll be presenting some methods of how to improve one of the key parameters that will enable kind of faster optical communication speeds. So the overview of my presentation, I'll start by giving a rather quick description of the fiber nonlinearity model and how to model these, how these links have been modeled over the years. Then I'll go into some digital fiber nonlinearity compensation techniques. So these are techniques that you would use using DSP either before the electrical to optical conversion at the transmitter or after the optical to electrical conversion stage at the receiver. And then at the end I'll present some optical nonlinearity compensation techniques. So these are techniques that are done entirely in the optical domain without using electronics or digital processing. So in the context of this presentation, it's mainly going to limit it's going to be limited to coherent systems. So these are the systems that are really becoming more and more used in optical communications, less so 10 years ago and only started probably 2006. But into the future, these are the systems that will drive or enable the capacity limits to keep improving. And by no means do I try to make this presentation sound like it's kind of all-inclusive. These are methods that kind of I've considered. I haven't done research on all of them. I've gone broader than my own research, but yeah, by no means do I pretend that this is an exhaustive search of all the methods available. Okay, so I'll start by talking a little bit about this curve. Anyone that's people in this curve is probably more famous to the information theory people for being the Shannon's capacity. So there's some bound that limits the maximum bit rate or the maximum spectral efficiency that can be achieved in any link. And this is governed predominantly by the noise, which is usually modeled as additive white Gaussian noise. However, in the optical channel, because optical fibers have a nonlinear property, which increases with increasing signal power, you cannot indefinitely increase the capacity limit by simply increasing the power. So eventually you get to some point where it kind of plateaus or it curves off, and then if you try to go higher than that, you actually lose performance, and you have to play some tricks to try to get your performance back. Where exactly this falls off depends on a lot of parameters, such as the type of signal you're using or the optical link that you're using, and various parameters that I'll be discussing a little bit throughout the next 40 minutes or so. So looking at the fiber model, any span of transmission fiber, so this might be some, let's say 80 kilometers piece of fiber, can be modeled by initially a nonlinear step, which applies this phase retardation to the signal that's proportional to the power of the signal. So that's proportional. So A with respect to T is the optical signal here, and P is just AT squared. So here we have a phase shift which is proportional to the intensity of the signal. Now next we have what's called chromatic dispersion. And this is the fact that in fiber the different colors of light travel at slightly different velocities. And from a first order, the most dominant effect causes this quadratic phase shift across the different frequencies. So we can see here I've got these equations, this equation here written in the time domain, and this equation here written in the frequency domain, and that's just for ease. So this is the simplest kind of domain to represent these effects. And then, well, this can be in any domain, so I haven't, doesn't really matter, it's just the attenuation of the fiber, so you have this attenuation parameter multiplied by the length. So as the signal goes through these three steps, you get a nonlinear phase shift, you get a linear phase shift that's dependent on the color of light, and then you get some loss of power. And to accurately model a single piece of fiber, you need to do this repetitively over and over again. So there's no general solution yet that will let you model this fiber for any arbitrary signal and get a correct response at the output without doing numerical and iterative approaches. So you've got to go round and round and round. Now, in an optical link, of course, they are often thousands of kilometers, as Cedric has already mentioned. You clearly cannot go there with no amplifiers. So we have these things called optical amplifiers in the link, and so you can add these to the model. So every few steps, or when you get to when the attenuation is such that the signal needs amplification, we can model with an amplifier, and then we go into the next span and we start the process again. So you have this double two nested for loops kind of thing in your nonlinear modeling. So on that, this is kind of a good lead up or a good prelude to describing some of the digital techniques which were used, which are somewhat related to the nonlinear modeling. So here, what the inverse fiber model entails is that you have, you could do this at the transmitter or at the receiver. In this particular case, it's at the receiver. So you have a coherent optical receiver which maps the optical field into an electrical field, and then you have analog to digital converters enabling you to generate a digital representation of the signal, and then you can basically spin it through a fiber model. So you would have n would be negative n of your real fiber, d would be the negative value of d of your real fiber, and attenuation would actually be the negative attenuation. So in this case, the power as you propagate will go back up. So this is, of course, a digital link, so you can do anything you want. Such fiber parameters are clearly not possible in reality. So now these fiber models are very computationally intensive. They take a long time to run, and you need a supercomputer that's very, very powerful to even cope with one link in real time. So this kind of very elaborate method of nonlinearity compensation is clearly not feasible for any real links. So what we can do here, we can start, well, all right, so let's consider the case of a dispersion compensated link. Now these are predominantly how links looked up at least to about the year 2005. So we have what's called dispersion compensation fiber. This is a fiber with a parameter that's got negative value of d, so it compensates for the dispersion of the link. So in effect, each fiber span has its dispersion compensated. And in such a link, we can approximate that all of that the dispersion is equal to 0, and all of the nonlinear effects collapse to a single module like this. So therefore, we're able to kind of approximately guess the nonlinear products with only a single step. And because it's only one step, we call this single-step nonlinearity compensation. So once we've reduced it to one step, the computation becomes trivial, yeah. So this is really a very small overhead on the system, on the digital equalizer. So the first time that this was presented or proposed was for a DPSK system using in a dispersion compensated link. And this was done in 2002 at Bell Labs. So of course, as I mentioned before, it completely ignores the effect of chromatic dispersion. So full nonlinearity compensation is clearly not possible anymore, as this is a very big assumption, but the benefits were observed in the experimental lab nonetheless. So it's shown to work well for low chromatic dispersion links, that is dispersion compensated links or links or links constructed with fibers with very low dispersions. Okay, so next we'll talk about how to implement this in the digital domain, which is kind of more practical for coherent, more modern coherent systems. So this is, I've effectively swapped the optical circuit diagram for more kind of signal processing things, where this is the signal multiplied by the conjugate to get the power, then you scale it by this some factor, and then you apply this to e to the, take the original signal and multiply it to e to the negative I x, where x is the compensation signal coming through here, and then that's followed by a linear equalizer. So this method was first proposed by Professor Kikuchi and by Arthur Lowry. Now, because the channel is memoryless, the computational complexity is very, very low, and it's trivial compared to the linear equalizers that are already used in these coherent systems. So just like before, it's only good for low dispersion links. And later on, we showed that by placing a low-pass filter here, that improves the performance of these single-step methods. Okay, so to quantify kind of the benefit that you can get, we can use numerical simulations, for example, where the optical link is simulated in a very elaborate method to guarantee, or with very short steps to guarantee us good accuracy, and the compensation methods are done with this very coarse single-step method. So there's the link there. It's a typical dispersion compensated link, 800-kilometer link with some dispersion pre-compensation, and then a typical link with some residual dispersion per span. So you can see here, if we look at optical power and we look at on the x-axis and the received quality on the y-axis, we can see here, so at low powers, the signal is predominantly limited by noise or amplified spontaneous emission. And here the system with and without precompensation work about the same, because there's no fiber nonlinearity. As you start to reach high powers, the signal without precompensation falls over, and the compensation gives you your benefit. So it lets you reach a higher power before it falls over. Because it's approximate, it does fall over, and when it falls over, it looks exactly the same shape as an uncompensated case. Now that works very well if you only have a single wavelength channel, but most optical systems operate, of course, in a WDM regime where you have lots of neighboring wavelengths spaced, let's say, at 50 gigahertz apart. And in such a case, the benefit that you can get, so that's the original graph is shown here in green, faded, not to distract you, and the red is what you can get from this method once you have kind of 8 WDM channels. And clearly it's not very much, because the system is limited by cross-phase modulation. So this is an effect where to illustrate this effect, we take a modulated signal with NRZ modulation. So this is the modulation that is typically used prior to 2005. Just for comparison, it just goes on and off. And if you take a fiber, if you go through a fiber or a link without any dispersion, the signal is mapped completely onto the probe. And if you apply this phase modulation that I talked about earlier, you can completely clean up the signal again. So what then we propose is, in order to, just like compensating from self-phase modulation or the single carrier effects, we propose to put this method out the front of the demultiplexer and compensate for cross-phase modulation. Now, in a dispersive link, the mapping of cross-phase modulation is actually very narrow band. So therefore, we need this low-pass filter to be rather narrow, on the orders of hundreds of megahertz for 10 or 100 gigahertz signals. So you can see here, by using this low-pass filter, we can clean up so this should be just an unmodulated probe, and we can see this signal here cleaning up the unmodulated probe a little bit. So we're going to quantize the benefit of putting this single-step nonlinear compensator out in the front. So here we see a single-channel performance, and here we see the performance if we put some legacy channels in the system. And we can see here, if we have cross-phase modulation, we can improve the performance by almost 2 dB. And likewise with an OFDM signal, for example, we can still go get around 1.5 or 1.3 dB. Now, in both these cases, I've capped the single channel performance. As you can see, we're still a long way away from single channel performance. So this cross-phase modulation compensation technique works a little bit, but by no means kind of gets close to compensating all of the cross-phase modulation. Now, because we can compensate for chromatic dispersion with digital techniques these days, often people are proposing to remove all of the DCF. So you can and to compensate for chromatic dispersion using digital signal processing. This decreases the cost of the link also, so it decreases the initial outlay. And it's also been shown that removing the DCF actually generates better nonlinear performance for high bandwidth systems. So in such a link, it was proposed by Kelly and Kim Roberts in 2005 and 2006 to use this split-step model at the front of the link. So you generate your bits, and then you pre-distort the signal before you go to your DAC, which drives your optical modulator. So you pre-distort the signal for the link. And later in 2008, it was proposed by Dr. Lee and Dr. Ip that this system was moved to the receiver, because at the receiver you're in a better position to estimate the link that you've just gone through. So in such a system, the typical implementation, like the model before or the equations that I showed before, it's easier to compensate for chromatic dispersion in the frequency domain. So we use an FFT to convert to the frequency domain, compensate for chromatic dispersion, use an IFFT, convert back to the time domain, and then compensate for the fiber nonlinearity. Sorry about that. That's kind of stuffed up the slide a bit. But that is pretty much like the previous slide. So this is squaring of the power, scaling factor, and phase modulation. Okay. So now this system here requires at least one backpropagation step per span, and in some of the estimations on the computational power, it was still estimated that around somewhere between 50 to 100 times the computational complexity of a linear dispersion equalizer is required for one step to compensate for one step per span for, let's say, a 20-span link. So that's a little excessive and beyond the current capabilities of DSPs. So we need to further simplify that. And one of the methods that was shown to be capable of this is to use this low-pass filter again. So once again, we introduce this effect of a low-pass filter, so to only encapsulate to remove the high frequency intensity fluctuations because they are suppressed by chromatic dispersion anyway. And this allows you to compensate for multiple spans per step. So in some simulations we did here, well I did, we can see here that you can take your system. So here on this gap here is 0 steps, so that means just linear compensation, and as you increase the number of steps, the performance improves. Now, what's interesting to see is that the performance improves almost on this linear line if you have a system without the filter, but once you put the filter in, the performance improves very, very quickly as you reach, this is a 40-span link, so as you reach, let's say 10 or even 5 spans, so that's only requiring, so that's a reduction by a factor of around 4 or 5. The performance starts saturating around here, so that, and the performance there is comparable to 1 step per span. So you can reduce the number of steps that are required by a factor of around 5 to 10 by adding a low-pass filter in. And here again, to quantify the benefit that you can get, this is in a single wavelength system. We can increase the nonlinear threshold by over 3 dB, and the same for QPSK. Okay, so we've talked a bit about how you can model and the ways of simplifying this technique called digital backpropagation, but also it has its limits. Now you would think that since chromatic dispersion and fiber nonlinearity are both deterministic effects, we should be able to fully predict everything that happens. And if we did that, if we encapsulated the entire optical signal and we built a very accurate model of the link, with all the with unlimited computational power, we should be able to compensate for all of it, and the performance should just increase and increase. And that was not found to be the case. So it's found that the performance did increase a lot further, maybe by 10 dB or so, but then it eventually fell back down again. And this is detailed in Dinesh Rafiq's paper in Optics Express, where he basically backpropagated his entire signal through a fiber, and this effect can be drawn to the fact that you can have ASE beating with your signal, and that effect eventually becomes stronger than your signal, and that's why your signal starts falling over again, even if you have all the deterministic effects covered. So of course the ASE component is random, and there's no way you can predict where or how much or what kind of the ASE looks like. So digital backpropagation has kind of a large potential, especially as the power in digital techniques and signal processing is forever increasing, but in order to compensate for cross-phase modulation especially, you need a large number of interconnects and you need a large number of steps. So, but even then, assuming that we eventually overcome these issues, it's a big if, but assuming that we do, this method is still not suitable for mesh networks because the wavelengths can be switched and your neighbors may change. So we have a look at this pilot-based method, which I think is quite interesting. So the prelude is that in 2008, Sander Janssen proposed that we can use a pilot to compensate for initially laser phase noise. Oh, sorry, the formats can chuck my symbol there. So that square is your signal. So what you do is you transmit a pilot with your signal. You remove the pilot with a low-pass filter, and then by doing that, it becomes very easy to get the phase information on that pilot, and then you multiply rather the phase information of the pilot with your original signal, and that compensates for the phase noise on your signal because you assume that the sidebands have the same phase information as the pilot. Now, so the initial proposal was for laser phase noise, and laser phase noise is typically a very narrow band effect of maybe 3 or 5 megahertz. So the filters used were very, very narrow. However, we can also extend this to fiber nonlinearity. Fiber nonlinearity is a much more broadband effect, so therefore we needed to move the signals further away from the pilot to give the pilot more space to allow our filter to properly isolate the nonlinear products or the nonlinear phase shifts. However, the initial performance improvement that was achieved with this was not huge, and this was mainly due to the fact that you have this self-phase modulation effect. And that's a very, very broadband effect over several gigahertz. And there's no way you can leave a gap around the pilot of that much without kind of completely destroying your signal, or your spectral efficiency rather. So you can see here in a single wavelength case, the pilot or the carrier there is not very broadened. All you have is this big pedestal of noise. And in a multi-wavelength case, in 7 wavelengths here, you see this pedestal of noise is still there, but the pilot also has phase modulation. So here this is what we recognize, and what we say is, well, we need to somehow clean up this pedestal of noise with a different technique, but we should be able to take out the phase modulation which has been caused by the neighboring channels on the pilot and also the signal fairly well with this method. So we're going to compensate for only the cross-phase modulation and not the self-phase modulation. Okay. So this is an experiment that we did to kind of prove as a proof of concept to show that this method works. I won't go through all the details of the transmitter, but basically we generated 7 wavelength channels, and we're mainly interested in the middle one, and we're trying to kind of compensate for the phase noise of the middle one, getting the interference from the 3 either side of it. So this is the optical spectrum that we transmitted through the link, and that's the receiver setup. So we use this optical filter here to select only the middle channel, and this is a single polarization experiment. So we only need 2 outputs of the optical hybrid. Okay, so the offline digital processing comprised of, firstly, this single-step intensity-based self-phase modulation compensator, which is kind of like the single-step inverse model approach. And then we use this pilot-based approach to compensate for the cross-phase modulation, And then we used a typical one-tap equalizer to equalize out the phase response, or chromatic dispersion response, out from the channel. So with no compensation, that's still with a one-tap equalizer, but without any nonlinear compensation, we get this line here. So this is the kind of the noise limited performance at low powers, and at high powers we have the nonlinear limited performance. Now, if we only use the intensity method to compensate for our self-phase modulation, we get around a 2% improvement in the nonlinear limit. And if we only use the pilot-based approach, we also get around 2 dB improvement, but we lose a dB on the noise side because we need some power and some spectrum in order to send this pilot through. However, if we use both, if we use self-phase modulation and the pilot approach, we still lose this 1 dB because of the pilot being there, but we gain actually 6 dB on the nonlinear side, because now we're able to compensate for both self-phase modulation and cross-phase modulation. And this actually gets us around 3 dB away from the single wavelength situation. So that shows that we're compensating for around half of the cross-phase modulation in terms of intensity. So this is kind of like a summary slide. You get 1 dB, so you should get 3, but you actually get 5. So this dB improvement in the total margin. So this shows that these two methods kind of have synergy benefits. So using them together is better than using either, is better than just the simple sum. So it's a case where the whole is more than the sum of its parts. And so that was for a dispersion managed link there. And this is for a dispersion unmanaged link. These results were done at Nokia Siemens Networks. So you can see the power curve here. So it shows a similar thing where, so these are not dispersion managed, though the self-phase modulation technique was changed to a multi-step inverse fiber model or digital backpropagation. The digital backpropagation curve improves the performance by roughly around that much. The cross-phase modulation is shown by the orange curve, and that increases it but less. And the sum is above all of them. So here we can see, once again, in a dispersion unmanaged case, you still have synergy benefits with an inverse fiber model. Okay, so now I'll move on to the optical techniques. And this will incorporate, here I'll discuss some mid-span spectral inversion, some end-link compensation, and a subcarrier symbol array. Okay, so I'll start with optical phase conjugation. So optical phase conjugation is where you go halfway, and then once you go halfway, you conjugate your signal, and then you go the second half. So the idea here is to use, so that's inverting the spectrum. So the idea here is to use the second half of the link to compensate for the first half of the link. So here, in this particular experiment, we tried to go through a 10-span link of just 80 kilometers without any dispersion compensation as the reference link. And then we went through a case of an optical phase conjugator. So we went through 5 spans, your optical phase conjugator using highly nonlinear fibers, and then a second half of the link. So here we see just the back-to-back case. So this is without the link itself, just the back-to-back performance, and then followed by the back-to-back performance with an optical phase conjugator. So this shows here the degradation caused by the phase conjugation process. And this is the link performance. So here is the launch power through the link. Of course, it's not relevant when you're not going through the link. And there's the performance for optical phase conjugation. So we see here, because the phase conjugation causes some power loss in the middle of the link. We see a small penalty on the noise side, but we can gain a very large amount on the nonlinear side. So on the high powers, we can see here the link is, if the second half of the link is effectively compensating for the first half. And for this particular signal, we can see in the OSA, it's probably too small for you guys to see. The signal was 160 gigahertz in bandwidth, carrying 1.2 terabit per second, 600 gigabit per second signal on a single polarization. And so those results for a single polarization, you can actually replace the optical phase conjugation module by a module that looks like this, with an optical recirculator and this loop here, which makes it polarization insensitive and usable for a polarization, that kind of polarization multiplex signal that's kind of more commonly used. And we've got experimental results to suggest that very similar benefits to those shown in the results previous are capable simply by changing the signal to a polarization multiplex signal and subbing this in for the conjugation module. Okay, some good previous works. This paper here is a very kind of detailed paper that goes through and quantifies, if you had an ideal optical phase conjugator, how much benefit can you get in terms of nonlinearity compensation throughout the link. Like I've already I've flashed up quickly on the slides before, the compensation is not perfect because it's impossible to fully match up or phase match the second half of the link to the first half. So you're not going to get full nonlinear compensation, and this paper here quantifies how much benefit you can get in a very kind of rigorous mathematical way. And a second paper here, this also goes through, this was actually done by our lab, this quantifies the requirements on your optical phase conjugation module. Now I don't have, this is a piece of work that was never done in our lab, but is interesting nonetheless, so I've put it in, and I've had a kind of look at it briefly. Now you've got, in this case, rather than using your optical phase conjugation module in the middle of the link, which might be in the middle of the ocean if you're in a submarine link, it might be in the middle of the desert if you're in a long-haul terrestrial link. So my point is, it might be in a location where power and servicing might be very impractical, and so it's not really desirable to build a link with a complex optical module out in the middle of the field. So alternatively, you can try to move that to either the transmitter or the receiver, where you're guaranteed to have an abundance of power. Now, because you've no longer got the second half of the link to mitigate the effects of the first half, you're going to have to artificially create some nonlinear module that's going to create some both some chromatic dispersion and some fiber nonlinearity that will compensate, or at least partially compensate, for the link that you're going to go into. Now the challenge here of these methods is really to go into the module that you're going to add at a very high power to minimize the effect of amplified spontaneous emission or optical noise. Because if you go through the same link, then you're getting no benefit at all, because what benefit you gain in nonlinearity performance, you'll lose in noise performance. So of course the second challenge is also to have the nonlinear distortions and the chromatic dispersion very matched to your link to maximize the potential, to maximize the benefit that's gained from these methods. I don't have any results to present on that, but some papers that are interesting. So Mark Pelusi That's Clio hasn't happened yet, so this might not be available online yet, but he has a paper at Clio this year experimentally demonstrating a polarization multiplex DPSK. That's a very twitchy system, I know, because it wasn't coherent, so he actually had to play with polarizations a lot, but a lot of fun for him. Anyway, and another paper, this is a simulation paper on optical backpropagation. So this is an interesting kind of hypothetical paper because it proposes that you could use a very high dispersion, some very high dispersion sections and some very highly nonlinear sections to mimic the actual link. So almost to do backpropagation, but do it optically. So in this case, you could easily run through multiple wavelengths, or a single wavelength or a band, any bandwidth you wanted with these optical techniques. They're not bandwidth limiting, and nor do they consume a huge amount require a huge amount of multipliers. So he proposes using some exotic fibers and some fiber Bragg gratings, some other materials, or a mixture of a whole lot of things, but the challenge is kind of there. Of course, you could do anything really because it was simulation, so the challenge really is to find suitable set of materials to do this with. Okay, so this is the final method. Thank you for being so patient. Okay, so these papers here have shown that the nonlinear limited performance is somewhat dependent on the symbol rate of the subcarrier. So in this particular case, I'll go on here. So there's a summary of the results there. So in this particular case, this is what we're talking about. So you've got, let's assume that we want to fully load up the optical band with the maximum amount of signal, let's say for a terabit per second a channel or beyond. We'll have to use multiple optical carriers. So in this particular case, I've just put the transmitters next to each other, and I've made the symbol rate equal to the subcarrier spacing. So this effectively uses Nyquist pulsing and has zero gap. So in a practical system, probably you need 5 to 10%, but this is an idealized kind of lab test, so we didn't need that. And what I did was I changed the subcarrier spacing and hence also changed the baud rate. So I maintained the spectral efficiency to be constant, and I used a QPSK modulation format. This is a numerical simulation, by the way. So we can see here that this is for 800 kilometers. If you go a very low subcarrier spacing, slightly less than 1 gigahertz, then the performance is very poor, and that improves and gets to around optimum at around 6 or 7 gigahertz, and that falls off again. Now for a longer link, we can see that obviously the net performance is worse, but the interesting thing here is that the peak of this curve is at a different point. So the peak at this curve is now only at 3 gigahertz. So for longer links or for more dispersive links, you need a lower symbol rate rather than a higher symbol rate, as some intuition may suggest. So for the case of 3,200 kilometers, actually, if you wanted to go at 100 gigabaud, that gives you quite a large performance penalty. So you don't want to do that. So it's not, this simulation set here shows that it's not optimum to perpetually increase the baud rate. And this, like I said, seems rather counterintuitive, because you would think with a larger baud rate, you would get kind of a shorter correlation length, nonlinear correlation length, and the performance should improve. But this kind of, these slides here tell a story in that if you have a very high baud rate, you have very low intensity fluctuations at low frequencies. But once you go through some dispersive fiber, your high baud rate signal increases, gains a lot of distortion because it's so dispersed. So your signal becomes very quickly looking just like noise. Whereas if you have a low baud rate system, the signals kind of hold their form. They keep looking like what they did originally, and they do not increase significantly in intensity fluctuations, particularly at low frequencies. So here, as we go through more and more fiber, we can see the low frequency intensity fluctuations are actually highest now at the 100 gigabaud case and lowest at the 6.25 or the on the 6.25 gigabaud case. So that's why the 6.25, and for the longest link, the 3.125 systems operate the best or have the best performance. Okay, so that's the end. Just to summarize, nonlinearity compensation is needed to increase the capacity times distance product, but no readily implementable kind of nonlinearity compensation techniques have really been used. Each have their advantages or show promising results have been generated, but are not necessarily very practical in a real system. And in the future, we may need multiples of these techniques to give you some significant performance increase. Having said that, Google people might know this better than me, so I might be wrong here, but to the best of my knowledge, nonlinearity compensation has never really been used in any commercial systems. Apart from kind of using intelligent link design, like in the case of NRZ, or indeed in Coherent case, where you're using taking the DCF out, for example. Apart from that, we really haven't specifically looked at how kind of implemented specific techniques to improve the nonlinearity performance. And that could be because it's quite hard, and it's quite hard to get significant benefit. So maybe a good starting point is to take the links that we have and to look at optimizing the signal, like changing the symbol rate, like in the final demonstration there, as a first step to building kind of systems which are more tolerant to fiber nonlinearity. Thank you very much.